Okay, I want to just comment briefly on the method we've been using in this class, and probably the method you used in your differential equations class for solving these differential equation systems. So we'll compare what we've been doing to what I'll call the classical solution for the method you used in your differential equations class. So in the previous example, the system had the following differential equation using our operator notation. 1 over RC x of t. And we were interested in the output with the input x of t equal to u of t, and we had the initial condition, actually y of 0 minus, in this case it's equal to y of 0 plus, because it was the voltage across the capacitor, and so it won't change instantaneously as long as the input doesn't involve an impulse. In this case, you found the homogeneous solution, or sometimes called the natural response. So I'll use that term here, natural response. And again, this has the same form as our zero input response. Okay, again, it would typically be a sum of mode terms. The forced response is the response to the input. In this case, x of t is a unit step, so for t greater than 0, the input's just equal to 1. And then the forced response using the method of undetermined coefficients would actually take this form. It would just be equal to 1. And you can plug that into the differential equation above and see that this actually satisfies the differential equation with this particular input. Notice this is different than the result we got with convolution. Our convolution result, the zero state response, included a decaying exponential term, and that was necessary so that what we get from the zero state response is a solution whose initial conditions are 0. Okay. In your differential equations class, then you would actually combine the natural response and the forced response to get the total response. Y of t is c e to the minus t over rc plus 1. And then you would apply the initial conditions at this point, applying the initial condition that y of 0 is equal to 2. We see that c is equal to 1, and you get as the solution e to the minus t rc plus 1 for t greater than or equal to 0. Okay. And this portion is what would be called the natural response. This is called the forced response. Again, the natural response and the forced response are not quite the same as the zero input and zero state responses. Our zero state response was 1 plus an exponential term. Actually, it was 1 minus an exponential term. And our zero input response was 2e to the minus t over rc. In our method, our zero input response actually satisfies the initial conditions. Our zero state response will always satisfy the initial condition that y of t is equal to 0, because that's what zero state means. So again, some subtle differences here. We get the same result using the classical method, where typically your initial conditions are applied at t equal to 0 plus, just after the input starts. In our method, we actually can apply the initial conditions at 0 minus. Usually in circuit analysis, it's a little simpler to determine the initial conditions at 0 minus before the input is applied. And then the other difference is, our zero state response we get via convolution, which at least theoretically allows us to calculate that output for any input, whereas typically in your differential equations class, you're kind of guessing at the forced response or the particular solution.